Good morning, everyone. Welcome back to Early Morning Calculus. We are sort of here. A few technical difficulties this morning, but I think we'll be okay. And this is what we have planned for Wednesday, April 9. Time is flying. Winter will come back. Sort of feels like it already. Okay, what we have to do is finish the 10.1 section, and we are going to go into 10.2, and that's working with parametric equations. And of course, if you have any questions from (11.10), we can look at some of those as well. In fact, going back to 11.10, I don't recall if there were some evens in there. I believe we gave you even answers already, but I will double check.
Looks like
54 was even, wasn't it?
Yeah.
I don't have the answer to that one. Do you have the answer? 54? Okay, I guess we'll never know. Okay, do you have any questions from 11.10? Anything there that you weren't sure exactly what to do?
Number 11.
Number 11? Okay. Now this one they wanted you to come up with a Maclaurin series from scratch. And what's the difference between Taylor series and Maclaurin again?
Maclaurin is a specialized one.
Yeah, Maclaurin is a specialized Taylor. The center has to be at 0. Where Taylor says the center is at any real number A of your choice. So this time the center has to be at 0. So just as a reminder, this is 11.10. Problem number 11. The function originally was sinh of x. Now, if I'm looking for a Maclaurin series, I want to get this f of x to look like c0 plus c1 times x plus c2 times x squared plus c3 times x cubed, and so on. However, both Taylor and Maclaurin had a way to come up with a coefficient. See, the nth term would look like this for Maclaurin. And how does one get c sub n? And that's where the work is involved. You take the nth derivative of your function f, evaluate it at 0 if it's a Maclaurin, and divide by n factorial. Okay? So that's the work, trying to come up with this. And if you can get that, it's not too bad. Well, if I need an nth derivative, then we better start doing some derivatives. And this one works pretty nicely because the derivative of sinh, you remember that from Calc 1? Right? And what was the derivative of cosh? Calc 1. Still part of your book even if you didn't remember. It's actually just plain sinh. It was a little different than the sine and cosine. Didn't have to change signs. And f triple prime is back to cosh again. And the fourth derivative back to sinh again. So this problem isn't too bad to do because the derivatives are easy. Just back and forth between sinh and cosh. Of course, what I have to do is evaluate each of these at 0. So the question is, what is sinh of 0? Well, if you didn't know, you could look it up. You could do it on your calculator. Of course, I don't know, that's asking quite a bit. I don't know, I wouldn't expect you to do that because, I mean, that might take a little effort. Sinh of 0. Yep. F prime of 0 is like taking cosh of 0, which is 1. Okay, now that we know, I guess F double prime then is going to be back to 0, F triple prime is back to 1, and the fourth derivative, evaluated at 0, is back to 0 again. Okay, we now start writing out that series now that we know what the coefficients are. So I claim, therefore, that sinh of x is like taking C0 is 0 plus what's C1? Well, C1 is 1. And you got to divide by 1 factorial. Actually, that's the way it is in general. And then the x starts, right? But the next one is 0 over 2 factorial, and then it's x squared. The next one would be 1 again, but that's over 3 factorial, and that would be x cubed. The next one would be 0 again, but that would be over 4 factorial, x to the 4th, and so on. 1 over 5 factorial, x to the 5th. So you notice that every other term is going to drop out, isn't it? So basically what I have is x plus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th, and you can see just the odd powers are going to remain, right? Are we ready to convert to summation notation? I think so. And I decided to go from 1 to infinity because the exponents are 1, 3, 5, okay? You can go from 0, but I think from 1 to infinity treats this one pretty nicely, because then the power is just x to the what? I've got to get 1 and then a 3 and then a 5, right, for the exponents. So this is first term, second, third. Can you see a pattern here?
2 minus 1.
Yep. You have to take twice in and subtract 1. Won't that do it? 2 times 2 is 4. 4 minus 1 is 3. Good. 3 times 2 is 6. 6 minus 1 is 5. There's the pattern for the exponent. Now, what else do we need? Well, I think every term has a 1 on top, right? But what do I have to factorial on the bottom? The same number as the exponent. So it'd probably be 2n minus 1 factorial. Is that anywhere close to what Bob got? Or did he start at 0? We can do it that way. If you want to start at 0, which is our custom, how would we have to adjust? Well, then up here, see, this is the 0 term, the first term, the second term instead, right? So what do you have to do to 0 to get 1? Add 1. But what do you do to 1 to get 3? You can't add 1 again. You got to double it and add 1. So if you did this, it's going to be 1 over 2n plus 1. And x to the 2n plus 1. Same series. It's just that you start at 0 instead of at 1. Did Bob pick one of those, or?
It started at 0.
He started at 0? Figures. That's because I started at 1. Do you agree they're the same, though? Okay. So this one worked out fairly nicely because the derivatives of sinh and cosh just alternate, so the derivative is not a big deal. But you did have to remember how sinh and cosh go. But I thought, well, if they forgot, they probably could look it up. Or do it on their calculator, or something. Okay, anything else besides 1110? Finishing up on Taylor and Maclaurin series.
59.
59? Okay. It says use multiplication or division of power series to find the first three non-zero terms of the Maclaurin series for this function. Okay, I think what they're saying is the function that's given, this is 59, y equals e to the minus x squared times cosine of x. I think they're saying that each piece has a series to go with it that we could probably find in the table. But then I have to take the series and multiply them together to get a new series. So let's go back and find the series that's represented by each of these. Well, I don't have one for e to the minus x squared, but I do have one for e to the x, and it's on page 743. And the series would be n running from 0 to infinity of x to the nth over n factorial. So I want to first convert this to a series e to the minus x squared instead. Okay, how would I adjust this series to make it fit that? Remember how we did that? Wherever you have an x, put minus x squared there instead. So it would be minus x squared raised to the nth all over n factorial. Which we might rewrite as minus 1 to the nth x to the 2n all over n factorial. So I've got a series for e to the minus x squared, right? Okay, I think we can get cosine x series directly. N runs from 0 to infinity, and it's minus 1 to the nth, and then it's x to the 2n, and then it's 2n factorial. Okay, that's right off the table from somebody else's work for cosine. Okay? Now the instructions are, they didn't say write this in summation notation. That would be quite a feat. They just said find the first three terms of this series that are not zero. So I'm going to start writing out some terms of this series. You know, start expanding that using this one right here, the one I just circled. Okay, if you replace n with 0, you get minus 1 to the 0, which is positive 1. You get x to the 0, which is 1, over 0 factorial, which is 1. So the first term of this series is 1. You buy that? Okay, the next term is going to be minus, because you're going to take negative 1 to the first power. This is going to be x squared, isn't it? Because you're putting 1 in for n. And the bottom will be 1 factorial, which is 1. So you just get minus x squared basically there. Now they want me to do 3 terms, right? But if you want to get 3 terms, you got to do more than 3 here, because there might be some terms that you can combine in the two. So you have to go at least 4, maybe 5 out here. All right, what's the next one? It's going to be positive because it's minus 1 squared. It's going to be x to the 4th divided by 2 factorial. Okay, next one is going to be minus x to what power? 6. And 3 factorial is 6. Okay, I'm going to do one more to play it safe. I know I only want 3 terms in my final answer, but you might see why I want to do more than 3 here, because I might have some terms out here that might combine with the first 3 in this one. And what would be the next power? I'm up to 4. N is 4. Yep, x to the 8th. And what's 4 factorial? Okay, that should be enough to get 3 terms when I multiply them together. All right, now let's expand a bunch of cosine x. If you replace x with 0, what do you get? Yeah, minus 1 to the 0 is 1. X to the 0 is 2 times 0 is 0. I think the first term of that is 0. I get 1. Of course, if you weren't confident, what could you do? Type that in your calculator and then let this be 1, 2, 3, 4. Or just make it expand it, okay? But you have to be a little careful, because when you type that in, it just wants to give you the answer, you know. What is the sum of the terms? Okay, the next one, I think, is going to be minus, isn't it? Okay, what's the power on x if I let n be 1? Yeah, that part is matching, isn't it? But what if I let n be 1 on the bottom? 2. Then I'm going to have a plus again. This time I'm putting in 2. What's x to the 2 times 2? And you can see they're sort of matching, except the bottom is going to be 24. Okay, next one. X to the 6, right? What's going to be on the bottom? I'm up to 3 now because I started with 0. 0, 1, 2, 3. 6 factorial. Is that around 620? 720. And then it's going to be x to the 8th. And I don't think we're going to need him, so we'll just leave it as, let's see, 0, 1, 2, 3, 4, that's 8 factorial, right? I don't think we're going to need him anyway. Okay, now what they want is the first 3 terms of the series you would get if you'd multiply these together. So what you literally have to do to get it is you have to take 1 minus x squared plus x to the 4th over 2 minus x to the 6th over 6 plus x to the 8th over 24, and you have to literally multiply it by 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 720, and so on. Okay? Now how do you multiply those? Well, it's distributive. In other words, you got to do 1 times each of these first, and then you got to do x squared times each of these. What if you took 1 times each of those? What would you get? 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 720, right?
Wait, what you just do?
1 times each of these, you know. Distributive. You know, FOIL, expanded. Now I got to take x squared times each of those. What's x squared times 1? What's x squared times x squared over 2? X to the 4th over 2. What's x squared? Oh, these are minus though. Minus there. Because it's a negative times this one's negative, that one's positive. How's that? Okay, now I'm back on track. Minus x squared times positive x to the 4th over 24 would be minus. And finally, minus x squared times minus x to the 6th over 720. Positive x to the 8th over 720. Okay, now I've got to do x to the 4th over 2. Well, x to the 4th over 2 times 1 is... What about x to the 4th over 2 times minus x squared over 2? Over 4. That's this one times that one. Minus x to the 6th over 4. Okay, what's x to the 4th over 2 times x to the 4th over 24? X to the 8th over. And the next one, x to the 4th over 2 times x to the 6th over 720. It's going to be minus x to the 10th over. Okay, now you say, how far do you have to go? Well, they want the first what? 3 non-zero terms? Okay, is there going to be a 1 that survives? Yeah, so I got 1 term, right? Okay, now the next term in line is going to be the one that has x squared in it. Is the x squared going to survive, or is it going to become 0? It's going to survive because I have minus x squared over 2 and I have later minus x squared. So wouldn't that be minus 3/2 x squared? That's this one and that one. So I got 2 non-zero terms, right? Now, does the x to the 4th survive? But do you see why I had to keep multiplying? Because there's 1 here, there's 1 there, and I get 1 here too. Okay, so your next term is those 3 together. I have x to the 4th over 24, I have x to the 4th over 2, and I have that one twice. So that's going to be 3x to the 4th. Well, we need a common denominator. It's x to the 4th over 24 plus 12x to the 4th over 24 plus 12x to the 4th over 24. That's the 3 I have circled. So this is my second, and this will be my third. So I have a feeling the first 3 terms are 1 minus 3/2 x squared plus what? Now, see, what you have to ask yourself before you say that's the answer is, could I get any more x to the 4th if I did more multiplying than what I did? And the answer is no, because the next term is x to the 6th, and he's just going to produce x to the 6th or higher. And the third term has an x to the 4th in it. So these are a little bit painful, because you have to expand each series and then start foiling until you get the first 3 terms exhausted. Is that what Bob had? Oh, well, we got to check it. I mean, good grief. Okay, the hardest part of the problem, trying to find Bob's answer. I'm in 11.2. Now I'm in 1110. What section are we in? Oh, I'm getting close then. And this problem was 59. Bob's answer, 1 minus 3/2 x squared plus 25 24ths x to the 4th. What do you think? Close enough? Aren't you glad they only asked for 3 terms? How would you like to get the first 6? Well, if you wanted to get the first 6, you'd have to get all the way to x to the 10th, wouldn't you? Because that would be the power on the 6th term, because after 4 comes 6 and then 8 and then 10. But you'd have to FOIL it enough so that every possible x to the 10th was written down. And you can get x to the 10th different ways. See, this x to the 4th times x to the 6th here, that would give x to the 10th. But so would x to the 6th times x to the 4th here. And so would x to the 8th times x squared. So you got to make sure you FOIL enough terms so all the powers for that particular term are exhausted and present. Okay? So that's how we can take 2 series that have summations and multiply them together to get another summation. You could do that with division too. But I wasn't quite mean enough to make you do 61. Because division of polynomials is not too much fun. Okay, what I'm kind of curious is, I wonder if the calculator could actually do this. You know, directly. Because on the calculator there is a function called what? Taylor? And you get to play with that on the project, of course, but I'm just kind of curious. I shouldn't do this because I usually get burned. And that's on national TV, and then I get embarrassed. Okay, under F3, there's a function called Taylor, right? Okay, what do I want to find Taylor for? Well, I want to find it for e to the negative x squared. And that's times, and I think it probably like the times sign, cosine of x. And then what's the calling sequence for Taylor? What do they want next? Did anybody try any of those yet? I think they show it on the yellow handout. And Taylor on the yellow handout is mentioned, I believe, on page 3. And in that bold section here, see it? It's Taylor. I got that. First you enter the function. I did that, right? Then what do they want? Function variable, so I better go, what next? X, okay. Then they want another comma. And then they want the value of n. Well, how many terms do I want? Where does Taylor typically start? 0. So what should be n to get 3 terms? 2? Seems right, doesn't it? Okay, let's put in a 2. And then what do they want? Value of a? Well, this is a Maclaurin, right? So the value of a would be 0. See, a is where the center of the interval of convergence is to be. Okay? And we'll press enter. Whoops. I only got what? 2 terms. How are they looking though? So I can adjust that. It must be on the calculator they don't necessarily start at 0. So let's go to 3 here. And then what happened?
Supposed to change it to 2.
Pardon?
You're supposed to change it to 2, but to 0.
it centered it around 3 because of where I put it in. You did catch that, right? No, I don't want to change that one. I want to change that one, right? Didn't I have you nervous for a minute? Not even that long. Okay, I try hard. Well, I guess it can't do anything past 2. Well, what's that saying? There must be some zeros in there? You say, well, we didn't get them. Well, we were multiplying by hand, remember? So let's try 4. There it is. 1 minus 3 halves x squared plus 25 24ths x to the 4th. That's what we got, wasn't it? It's pretty good. But do you understand what I meant when I said I had to go to 4 for what reason? Because when you expand it directly, you're going to have some zeros in there. We didn't expand directly. We expanded by foiling 2 different series. But if you expand it directly, then you're going to get some zeros in there. And that's why if you want to get 3 terms, it's not a big deal. Just keep changing in until 3 terms show up. So if we're starting at 0, it actually took 5 terms to get 3 non-zero terms, which means 2 out of the 5 were actually zeros, and that's why they weren't showing up if you just do a straight Taylor from scratch. See, this is doing Taylor from scratch like we did number 11. I have a feeling if I go to 5, I'm not going to add on to this because it's probably another 0 term. I don't know. Let's see. Yep, see, it didn't change because every other term is 0. But if I go to 6, I will get 4 terms. You say, well, why is it so slow? Well, you've got to think of what it's doing from scratch. You've got to find those derivatives, right, and evaluate them and plug them in. So theirs would be the answer to that problem, the first 4 terms. So if we expanded some more and FOILed some more, that's the term that should be next. Minus 331 over 720 x to the 6. You say, you mean on the project I get to find Taylor series this way? Yeah, some of the time. Have you tried any of those yet? Why would you? It's not due for a couple weeks yet. I mean, I wouldn't start if I were you. I'll make sure I warn you the night before it's due so that you can start looking at it, okay? When is it due? This yellow thing.
Before the final.
No, it's not due on the final. It's due before that.
It says that before it.
I said you could go all the way to the final? No, I didn't. I said the week before. The Wednesday before the final. And what date is that?
23rd.
I think it's 23, as in April. Okay, did you write that on there? April 23, so you don't forget? That would be a Wednesday. Now, it would pay probably, you know, to start looking it over occasionally. I mean, the first few pages are all about this Taylor stuff. Do it while it's fresh. And that way, if you run into some snags, you can bring it up. You know, Wednesday morning, it's going to be too late to bring it up. So you got to start checking. That's a hint. Okay, do you have any other questions from 1110?
When you do 6, do you use the Maclaurin series for like the one we got from Maclaurin?
No, they wanted you to do number 6 from scratch. Number 6 would be easier if I could go back to page 743. I mean, go back to the one we did in class. I'm sorry. But they actually wanted you to do that one from scratch.
The answer is different.
Pardon me?
The answer is different. What is it from scratch?
You'll get the same answer, but we did natural log of x in class, didn't we? And if you took that answer and adjusted it for this one, I think it'd be faster. But what they really wanted you to do, I'm just telling you what the instructions are saying, is start as if you don't have any log expansions. Now we did it for what, x minus 2 was it, or x plus 2? I forget which one we did in class. I don't think we did plain, or did we do plain natural log of x? Oh, but we centered it around a different number. Then we centered around 2. So you'd have to adjust for that. But that wouldn't be too hard to adjust. But the spirit of the problem, in answer to your question, was take it from scratch and center it around 0, as Maclaurin wants you to do. Okay? Any other questions? 11, 10?
Just go through 17.
Check 17 just to see what's involved. Now in 17, you're allowed to use somebody else's and build on it, right?
Oh, okay.
It says assume that you have the power series expansion. It says that in the directions. So they want you to take f of x equals cosine of x, and then change the center to pi. Now you know how to do that.
X minus pi.
Yeah, the question is that going to change the other part, the coefficients?
No.
So you say the coefficients will stay the same, but instead of being powers of x, it's going to be powers of x minus pi. You agree? That's all that changes? So what you're saying is, if you go back to 743, and this is problem number 17, you have a cosine of x series given. It's minus 1 to the nth, and it's x to the 2n, and it's divided by the quantity 2n factorial. Okay, that's centered at 0. Now I want to refocus it, or recenter it.
You zoom out a little bit.
Think it'd be easier to read? No, harder to read, but you could actually see it. Okay, center at pi. So what he's saying is, maybe I could just do this and say x minus pi here instead of x, but that part will not change. Is that true? Well, when you look at where this comes from, when you are centered at 0, see, in general you have to take the nth derivative, and it has to be evaluated where? At a, and then you got to divide by n factorial, right? Isn't that in general what c sub n is? So where does the a come into play? Only in the numerator, right? So you think the 2n factorial should be changed. No. Now, in this Maclaurin series, we were replacing a with 0 every time, weren't we? Now we're going to be replacing it with pi. So what you might want to do is say, okay, if f of x is cosine of x, and try a couple, f prime of x is going to be minus sine of x, and f double prime is going to be minus cosine of x, and f triple prime is going to be sine of x again, right? Okay, now to get the Maclaurin series that you see in the book, they're doing f of 0 every time, f prime of 0, f double prime of 0, f triple prime of 0. Well, this is 1, this is 0, this is -1, and this is 0 again. And thus, they came up with this at the top of the screen, okay? Now, what are we going to be doing? Well, instead of plugging in 0, we're going to be plugging in pi's. What's the cosine of pi? Well, it's -1, see? What's the sine of pi? Well, that's still 0. Won't change that. What about minus cosine of pi? That's going to be 1. And then this one is going to be 0 again. So what changed? Yeah, the signs on the terms are just going to be opposites, aren't they? Because on the original, we want the first term to be positive, and that would be the case because it's -1 to the 0. And then we want this one here to be negative, the second one, which would be the case. But here they have to be just the opposite. So would this be the right answer? Well, if I put in 0, the first term of the series is going to be, but I really want it. So maybe what we would have to do is this to make it fit. Okay, let's see how Bob did it, because there's different ways to do it. But I think you got to be careful. There can be some slight changes that can occur. And how you check it out is you go back and remember where the stuff came from. I should put a bookmark by that. Oh, this time I am. Okay, that was number 17. Yeah, Bob did exactly what we did. He made the change with an n+1 there. It's very subtle, it's almost easy to miss. Whereas the original had n. So you do have to go back and say, is there any change in basically signs or anything? Do you see why it won't change the denominator? Because only the numerator is affected by the a value. So whatever you have down here, you don't have to worry about. But what's up here, you got to check it. So that is the final answer. Just replace x with x minus pi and then see if anything else up here has to change. And that's easily done by a quick check down here. Okay, anything else from 1110? You actually tried some of these. Wow. I'm kind of stunned. You think Byron Center is working on these? Ah, there are some. I promise they are. They're not exactly calling in with questions, but well, they're maybe not up yet. Okay, can we leave 1110? The ideas are basically there. So what is a Taylor polynomial then? I mean, I've heard of a Taylor series, but what's a Taylor polynomial? It's a Taylor series which has a finite number of terms. See, a series by definition has to be infinite, right? But if you take 6 terms of a Taylor series, we call those 6 terms a Taylor polynomial with 6 terms. Okay? So is there a huge difference? No, but it's kind of important that you know when they say, find me a Taylor polynomial, that all they're asking for is a Taylor series with a finite number of terms in it, and they'll tell you how many. Okay. All right, we have entered the world of parametric equations, haven't we? And it was kind of fun, especially if you keep the leading cursor on your calculator. It's almost as fun as Pac-Man. Whatever that is. Okay, what we were doing was just trying to get used to expressing equations in parametric form, and then how do you convert them to the Cartesian that's equivalent to it. And we were playing with graphs, and we were in parametric mode, and I think I shifted mine back for the other class. I don't know. I better make sure I'm in parametric mode again. Okay, mode. Oh, I'm back in function. Got to get back to parametric. Okay, and I even have some stuff in there. Maybe we'll get to look at some of that today. Okay, well, we wouldn't want to give you too far a lead here. So, do you have the handouts, everybody? This is the one for 10.1. We did start that last time, but occasionally somebody skips class, but none of you did, so you all have that one. Okay, we're going to pick it up where we left off then. And where we left off was we were about to go to page 626, and we were going to look at problem 16. Okay, and trying to follow the instructions for problem number 16. Well, it's kind of similar to what we did before. It's just backwards, because in 5, I don't know what they're thinking, because in 5 through 10 they said, okay, you get to sketch the curve first, and then when you're done, change it to a Cartesian. Okay, this one they say, change it to a Cartesian first, and then when you're done changing it, then you may graph it. I wonder what the deal is. Well, maybe if you change it to a Cartesian, it'll be such a familiar equation, you can just sketch it without a calculator and you won't have to go through the parametric to see it. I don't know. Well, we'll find out. So on page 626, problem 16, we have the following parametric equations. One of them is x equals natural log of t. The other one is y equals square root of t, and t can be anything greater than or equal to 1. So there's the stuff for problem 16. Okay, in part A they want me to find the Cartesian equivalent first. Well, if there aren't any trig functions involved, then basically we take one of the equations and solve for t. If trig is involved, then we try to write an identity first from trig and then substitute, because it usually goes more smoothly. Otherwise you got to work with all that inverse trig stuff. For this one, which one do you want to solve for t? The first equation or the second?
Second.
Okay, second one. How do you solve that for t? Square both sides. So that was pretty easy, right? Now what do I do after I solve that for t? So you substitute in the other one, so you get x equals natural log of y squared instead. But now to get it in Cartesian form, we want to solve that for y. Well, how do you solve that for y? Pardon me? You change it to exponential form. So that'd be e to the x, if I remember my pre-calc right, equals, I guess, y squared, right? E to the x equals y squared. Oh, so what does that make y then? Square root of e to the x, which is like e to the x raised to what power? Which is like saying e to the multiply the exponents. Oh, sorry. Multiply the exponents. I'd say that should do it, right? All right, but I have one little issue here. I thought when you solve for y, you were supposed to go plus or minus. Why didn't I? Because I look back here, and y is the square root of t. So if y is the square root of t, and t is greater than or equal to 1, y can't be negative. Because the square root, by definition, is a positive number unless you want to put a minus in front, and there isn't one there. So that's why I didn't keep the minus, because y had to be a positive number. Okay? But you should be thinking about those things. So I did part A. That's the Cartesian equivalent. All right, now the question is, they wanted you to draw a graph. Is that an easy graph to draw? Well, it depends on whether you were alert in pre-calc. I remember that functions of that type tend to hit 0, 1. And they tend to go like this. But on these kind, you got to be careful, because you can only graph it when t is what? Greater than or equal to 1? Okay. And if t is greater than or equal to 1, the first number you may use is 1, and what's the natural log of 1? 0. So this part of the graph is not there, because under that condition, you can only start with x equals 0 and go from there. So I would say that that's probably the curve. Now, how many people are actually going to do it that way? Not very many. Because we love to let this calculator graph parametrically, right? So if we go to y equals, and in x1, we can type the natural log of t. And in y1 to go with it, we have the square root of t. And then we can immediately go to the window and make sure our t is starting at 1. Now how high can it go? Well, as high as you want. Well, you got to really pick something. You can't type infinity in there. A calculator doesn't like that. So maybe we'll just type in 50 or something and see what happens. Now, I've been playing with a t-step. What's the normal one for decent speed and decent resolution? 0.13. I mean, you don't have to use that. And then, I don't know, let's go. Well, we know we're not going to be in negative territory, so -1 maybe to 10 to start with. And -1 maybe to 10 again. And we can adjust that if we kind of go off the screen. Okay, we're going to graph that. And it's not exactly flying even with 0.13. It must be a steep climb, and it's getting steeper. It's slowing down. That poor cursor. He must have bought some bad gas. Probably paid $3.50 a gallon for it besides. Poor cursor. In fact, you can almost hear him swearing. Maybe that's why they call him a cursor. I'm just filling in while this thing is slowly climbing the hill. But does it look at all like what we just got by looking at the Cartesian version? Yeah. I must have run out of gas right there because I only put 50 gallons in. So the RV just ran out. Hopefully there's another station in the vicinity, but that's going to keep on going, isn't it? Okay, any questions on what's going on 16? I kind of saved that one because it's a good review of our samples we did Monday.
So why did it stop there?
No, it doesn't, because t is greater than 0. It keeps on going. And that's why if I were to draw it for you, I would start it at 0, 1, and I'd put an arrow on the end of it too. instead of a dot. Now if it said from 1 to 50, then I'd put a dot because it's going to stop when it hits 50, just like it did on the calculator. But when it says t greater than 0, greater than or equal to 1 I mean, keeps on going. You can show that by an arrow on the end of the curve instead of a dot. Okay, let's see what's in 627 problem 22. Well, you probably noticed up to this point parametric equations aren't too bad, and they're even kind of fun, aren't they? We got to take care of that. We can't afford to let you have fun in here. This is Calc 2. It's not fun, it's work. And okay, page 627, how are they going to ruin everything? Well, they say, pretend that this is a particle that's moving according to the parametric equations, and you have to describe the motion of the particle as t varies in the given interval. That means, yeah, you can do all that other stuff, but you're going to make an essay question out of it, and you got to write an essay on the movement of that particle. Now that'll kill it if nothing else will, right? Okay, here are the equations. One of them is x equals 5 sine t, and the other one is, nope, I'm doing wrong problem, that's 21. 22, x equals plane sine t, and y equals cosine squared t. And my parameter t is varying from minus 2 pi less than or equal to t less than or equal to 2 pi. Okay, but a particle is following this path. And I have to describe the motion of the particle. Well, it used to be harder than what it is now because we have a calculator with a leading cursor on. And notice what's going to happen here, and you got to include that in your description. Okay, going up to x1, we just want the sine of t. There it is. For the other one, we want cosine squared, so I have to do a parenthesis, cosine of t, another parenthesis, and square it, because that's the way the calculator squares trig functions. Okay, next I go to my window and set the t from minus 2 pi all the way to 2 pi. We'll leave the t step there, but I think I better go minus 10 to 10 just to play it safe at first. Minus 10 to 10 for both the x and y max and mins. It may not be exactly what I want, but I can fix it from here. Okay, let's watch what happens. Aha. And I got to write an essay about the movement of that particle. But at least with the leading cursor on, you can pretend that's the particle and it makes it easier to see what it's doing. But isn't it going back and forth over that curve? It's kind of a small curve though. We can make it better if we go to the window and minus 2 to 2 and maybe minus 2 to 2 should magnify it a little bit. All right, this time you got to watch because we got to describe this path in a nicely written essay. Okay, so here we go. It's starting the y-axis, goes down to the x, back to the x on the left, all the way back to the x on the right, back to the x-axis on the left, and then back to the y-axis and quit. Did you follow all that? Well, if that's too fast, you know how to slow it down. Just go right there and lower the t-step. 0.02. That's going to slow it down. Okay, there it is. Okay, now keep track. It's going to start at a point on the y-axis. We'll have to say what that is. Goes to a point on the x-axis. Come on, this is a bit slow. I mean, we're not 90 here. No, we're not doing 90 either. and then it goes all the way back to the x-axis, right? As soon as it hits it, it stops. Okay, now it went from the y to the x, right? And then back to the x again. You keeping track? Now it's going to go all the way back to the x-axis on the right again, following the same path all the time, right? Okay, so it went from y to x, x back to x, and then from x back to x on the right again. Now it's going to go all the way back to the x-axis on the left. Is it going slowly enough to remember all this? And once it starts reversing its path again, it should stop when it hits what? So it's going to end where it started, isn't it? Okay, that's all got to be in your description. Are we ready to write it? Okay. I hope you got a good memory. Well, you can always make it redraw it again if you forgot. Okay, so here's the description. And it's not just draw a picture either. But it did start here, doesn't it? Okay, you got to name the point where it starts. Well, how do I name that point? Well, it's going to start at minus 2 pi. So just plug it in. What's the sign of minus 2 pi? You're right, it's 0. What's the cosine of minus 2 pi? You're right, it's 1, but I have to... So it's going to start at 0, 1, isn't it? And then it's going to follow some path, which we should name if we can. And it's going to stop down here in reverse direction, okay? The question is, when does it hit that spot? Well, it hits that spot when y is 0, right? Okay, what would you have to put in place of t to get 0 for y? What's the cosine of things like pi over 2, 3 pi over 2, and stuff like that, that gives? So anyway, when this is 0, doesn't that mean t would have to be pi over 2, 3 pi over 2 or something? What sine of pi over 2? Or 3 pi over 2? Well, it's either 1 or... See, I'm just trying to figure out where those points are. Guess where the 1 is on the left. Now, if you have a little trouble with that, what you can do is go to your calculator and see what makes it stop right at the x-axis on the right. Now, I would guess that it's going to stop. See, it's starting at minus 2 pi, right? I think if it starts at minus 2 pi, I have a feeling it's going to stop at minus 3 pi over 2. That would be my guess. And you can see whether your guess was right, because now it should just do that little right hand jog and quit. Okay, I'm starting at minus 2 pi. I'm going to go all the way to minus 3 pi over 2. Did it quit? Okay, so now you know the angle you're working with the first time is minus 3 pi over 2. Okay, but you don't have to be quite that elaborate in your essay unless you want to get extra credit. Then you tell the value of t every time it switches direction. Okay, here we go. My description. The particle starts at what point? Zero, 1, and follows what kind of a path to the point 1, 0. Well, I won't know what that path is unless I maybe do what? Convert it to Cartesian, so maybe I can recognize what kind of a path that is. What do you think it is? Circle? Let's check. Remember, if there's trig involved, and that's kind of why I grabbed it, you start with a trig identity that relates sine and cosine together. Remember that one? Sine squared plus cosine squared is 1. Okay, what can I replace sine squared with if sine of t is x? What can I replace cosine squared with? See, it's not a bad conversion if you can remember a trig identity to make it easy to substitute. We get y equals minus x squared plus 1. That is no circle. What is that? Recognize it? Y equals minus x squared plus 1. That's a parabola with vertex at 0, 1 and opening down. Where have you been all my life? Isn't y equal ax squared plus bx plus c a parabola? Okay, so it follows a what? Parabolic. It then reverses direction. And if you really want to be elaborate, you don't have to say this part, but you can say, if you really want a great description, when t is what value? Minus 3 pi over 2. Remember, we're starting here, right? And follows the parabola back to what point? Where does it go? Minus 1, 0, doesn't it? It then reverses direction, and here is optional. You can say it when t equals what? Any idea what it might be? Well, it was minus 3 pi over 2. So the next one is going to go through with the 2 on the bottom would be a you believe that? Right at minus pi over 2, it's going to quit here and then head back. I have a feeling you're not going to add those. You don't like that, do you? Tell me exactly when it reverses direction. Well, we can verify that. That's how much of the curve we got if we went from minus 2 pi to minus 3 pi over 2. Now if I go to the window and change that to minus pi divided by 2, okay, getting closer to 0 now, it ought to go to the right, reverse, go to the left and quit. Here it is. I got to increase the t step. This is too slow. Okay, any day now you can reverse. I know it's a steep hill, but you can do it. Price you paid for gas, it ought to be good stuff. See, it doesn't stop there, right? But it should quit as soon as it hits the point minus 1, 0. See, if it quits there, that means it reversed direction at minus pi over 2, right? Because that's as far as I went. Okay. Back to the description. So I've got it going from 0, 1 to 1, 0 and back to minus 1, 0 again. So it reverses direction. And what does it do? Follows the parabola back to 1, 0 again, doesn't it? And when it then reverses direction, and you can say, if you want to, I'm just wondering if you can guess where it's going to reverse again. Well, it was minus 3 pi over 2, then it reversed at minus pi over 2, so the next time it's going to reverse is at, yep, So it then reverses direction and follows the parabola to what point? Now, did you keep track? It reverses direction, and in case your essay is getting a little boring, you could say it reverses direction yet again. Oh, you can spell again, right? Yet again. And that would be when what? Which you don't have to write, but you can probably tell me. And heads to what point? 0, 1. Ending where it started. So how's that for turning a fun section into a pain in the you-know-what? But they just want a complete description so somebody can picture in the mind what the particle's doing without seeing the picture. So can you picture that? So in your mind you got a particle starting at 0, 1. It moves along a parabolic path to 1, 0. And then it reverses following the path to -1, 0. And then it reverses and goes back to 1, 0 again. Then it reverses, goes back to -1, 0. And then it reverses, quitting at 0, 1, its starting point. Okay, so how many of those did I assign? 1. Good luck writing your essay. It must be typewritten with 1-inch margins on each side and 3/4-inch margins on top and bottom. You must use good English and good spelling, and it must be exciting enough to the reader that they actually complete reading it. Got the instructions? Okay, there's one more which is just kind of out of interest, plus I want to indicate something which might come in handy later. If I said graph that curve, you'd kind of laugh at me because you'd say, I don't think I can solve this for y, and I don't think you can either. You're right, I can't. But there might be a way to actually see this curve if we do it parametrically. Now, because of the powers on y like this, I have a feeling it's not a function. Because if it's a function, you got to be able to write it as y equals something. So I don't think that's going to be a function. However, parametric equations make certain curves, not every one, but one like this, possible to actually see. How do you do that? Well, you got to convert it to parametric form. And you said, we haven't done that. All the problems so far, you gave me the parametrics and you said go back to Cartesian. We haven't done this. Well, it's probably because it's the easier direction to go. And one way to go that really works nicely on this one is to pick either x or y. In this case, I'm going to pick y because there's more of them. And I'm going to let y equal t. Well then, x cubed would equal what with that substitution? T to the 4th minus 2t squared minus t plus 1, right? Which means x would become what? The cube root of whatever that is. And right there, circled before your very eyes, are two parametric equations. Well, nobody said the first one couldn't be t. And the second one's going to be the cube root of the quantity t to the 4th minus 2t squared minus t plus 1. And that's something I can actually graph on my calculator. And I might be able to see this non-function curve. Something that eluded us when we worked strictly in Cartesian. Boy, this is exciting. I can hardly wait to type it in. Okay, first of all, xt1, well, let me see, cube roots on this calculator, we usually do t to the 4th minus 2t squared minus t plus 1, and then we raise it to what instead? The 1/3 power? Okay, there's the x, right? And what did I make y? Just t. Okay. I may want to change the window a little bit, but let's just try the standard window first. F2, 6. Well, it's definitely not a function. I might be able to see it a little more clearly if I zoom in on that first portion. Yes, zoom box still works in this medium. That's kind of nice. And what I want to do is just see a little bit more what it's doing near the origin. So I'm kind of boxing in a section. Now if you want to make the box draw faster, go second arrow. Then it takes bigger jumps. Okay, I'm going to look at that much. Yes?
Can I see your y equals, because mine doesn't look like that.
Yeah, right after I press enter, we'll go back. Okay, here it is. And there's a graph of that curve. Good luck trying to get that curve in Cartesian. Well, you're not going to be able to solve for y because it's not a function. But did you notice also the change in pace in that particle? That's another thing I wanted you to see. I'm going to change the t step just a little bit, 0.9 instead of 0.13. Okay, now notice what it does as it turns corners and stuff. It could be some kind of a vehicle traveling. I think that was a bad t step. That's because I meant to go 0.09. Sorry about that. 0.09, not 0.9. Like that. Okay. See how it goes? And when it's on the horizontal, it just kind of zip, and then it turns a little and it slows down. I told you this was more fun than Pac-Man. We even get speed changes. Okay, he wanted to see what I typed in. There it is. So for y, I just typed in t. That's it. So what is yours doing?
I maxed my y mixed around.
Oh, did you get something?
Yeah,
Okay.
it was just basically, I think it looked like yours, except it was
Rotated
up instead of
90
exactly.
degrees. Yeah. Which would make sense, right? Because you changed the x and y around. Okay, so you were impressed with that, right? Depressed? No, just maybe pressed. Okay, the other thing we have to begin doing is that next little section, and that is the fun's over now, because the next section is how do you do calculus when the curves are given parametrically? What do you mean? Well, we're going to have to do derivatives, integrals, and that's in section 10.2. Calculus with parametric curves is the topic. Okay, the people here need that handout, so I will bring it to you. And hopefully we can at least see how to do a derivative today. And then on Friday we'll see how to do integrals. Okay, calculus of parametrized curves. I like that word I made up, so I use it. What happens when you start doing calculus of parametrized curves? Students become traumatized. So, you ready? Well, you know it can't last that long because it's 8:45 already. Okay, here we go. Finding derivatives of equations that are in parametric form. Here are the conditions. Here's parametric equation number 1. Here's parametric equation number 2. And here's parametric equation extra that you can scratch out. You don't need 2 of the y equal g of t's. Okay, then the function determined by these 2 parametric equations is said to be differentiable at a only if both of the functions f and g are differentiable. So we say the parametric equations are only differentiable at some t equals a if both pieces are. So if you can do one but not the other, then you can't get a derivative. But that's probably pretty obvious. The question is, how do you do it? Okay, I want to find the derivative dy dx, just like I always have, but the equations are in terms of t, and the objective is not to have to convert the equation back to Cartesian, even though we sort of know how to do that for certain cases, right? The object is to get the derivative directly from what you have, the parametric equations. Okay, but here's the key. If you want to do dy dx, doesn't that mean y is probably some function of x? You know, like y equals e to the 2x minus log of x or something. Okay, but x and y are both functions of what? T. Okay, thus y can be viewed as a composition of 2 functions. And whenever we want to do the derivative of a composition, we use the infamous chain rule. You say, well, I'm not sure if I see that exactly. Well, maybe y is something like 2x squared minus e to the x or something, right? But y is also some function of t. But x is a function of t as well. You know, whatever they are. Well, we're not really looking at that one right now. But y is a function of x, right? Y can be written as 2x squared minus e to the x. But x can be written in terms of t. So how would I find y if you're given this? You'd have to take all your x's and replace them with these t's, and then you can get y as a function of t. Wasn't that exactly how composition works? So let's suppose I wanted to find y of 1. That's t equal to 1. Well, wouldn't I first put 1 in for t, which would give me x, and then I'd take the x value and put that in here, and I'd end up with y of 1 when t is 1. That's composition. Well, how does composition work when you do derivatives? Well, I don't know if you remember this way back in Calc 1, but it's fairly obvious. If you want to take dy over dt, you can get that by taking dy over dx and multiplying it by dx over dt. You can see that's true, right? That happens to be Leibniz's version of the chain rule. But again, it's nothing that should throw you for a loop even if you forgot, because can you see this and that are the same? Okay, but what did I really want to find? I really wanted to find dy dx. I don't know why he's there. I really wanted to find dy dx in all this. So I take this and solve for dy dx, which means I have to take dy over dt, which is on the left, and divide it by what? I want to solve this for dy dx. So don't you have to divide it by dx over dt like that? And right here is the official formula. If you want to find dy dx and y is in terms of t and x is in terms of t, just take the derivative of y with respect to t and divide it by the derivative of x with respect to t, and you'll have the derivative of y with respect to x that you wanted in the first place. Okay, in case you dozed off, here's the official conclusion with everything in it. If x can be written as an f of t, and y can be written as a g of t, then the derivative is the derivative of y with respect to t divided by the derivative of x with respect to t. But then you'd say, well, how would Newton write that? Well, Newton likes to use prime signs, right? So for dy dt, what would he write? Y prime evaluated at t. And this would be x prime of t. But I can even go a little bit further, because what is y? So wouldn't it be really doing g prime of t and dividing by f prime of t? So different ways you can write it, they all mean the same thing. Okay, but this only works if f and t are both what? Differentiable functions. Okay, well, if that's the way you find a first derivative, how do you find a second derivative? Well, first of all, we recall what a second derivative means. Doesn't the second derivative, and here it is in Leibniz notation, doesn't it mean take the derivative of the first derivative? So couldn't I just simply say this is taking the derivative with respect to x of y prime, kind of mixing the notations together? Isn't that what the second derivative means? Take the derivative of the first derivative? Okay, now if we convert this to parametric form, we can first say this is therefore the same as the derivative of y prime over the derivative of x. That comes from here, just writing it as one fraction. dy prime over dx. Well then, according to what we just did, y prime is going to be in terms of t, and so is x. So what I have to do is take the derivative of y prime with respect to t and divide it by the derivative of x with respect to t. So this goes to here. Because if you want to do the derivative of y with respect to x, you do the derivative of y with respect to t over the derivative of x with respect to t. But I don't want the derivative of y, I want the derivative of y prime. So I do him with respect to t and divide by that. Or sometimes a little easier to follow if you say, take the derivative with respect to t of whatever y prime is and divide it by dx over dt, sometimes written that way. Okay, well, I want to try a little bit on an example. We won't finish this example today because it has two parts to it, but it says here's a couple of parametric equations, find dy dx and find the second derivative, d squared y over dx squared. And then when you're all done, find the equation of the tangent line to the curve when t is minus 1/6. Okay, I just am going to be content to find this. What does the formula say? Take the derivative of y with respect to t and divide it by the derivative of x with respect to t. Okay, here's x and here's y. On top is the derivative of y. What's the derivative of cosine? Minus sine. Minus sine of what? Same argument. And what do you have to multiply that by? 2 pi. Okay, denominator, do the same for x. What's the derivative of sine? And that'd be 2 pi t again, times what? 2 pi. Okay, well, fixing it up, what can you do? Cancel that, right? And what's sine over cosine? So it'd be minus the tangent of 2 pi t. There's your first derivative in terms of t. Okay, then how do you get the second derivative? Well, the second derivative, you take the derivative with respect to t of whatever y prime was, and then you divide it by the derivative of x with respect to t. So I already know the denominator, don't I? Because I already did dx over dt. And if I got it right before, then it should still be cosine of 2 pi t times 2 pi. But what does the numerator become? We have to take the derivative of the answer I just circled. What's the derivative of tangent? Secant squared. So this would be minus secant squared of the 2 pi t, and then times 2 pi. And again, these will cancel. And what would Bob do? He'd probably leave this, and he'd change cosine to 1 over the secant to make them compatible. That's just trig. And then if you invert and multiply, you get minus secant cubed of 2 pi t. And there's your second derivative. So the first derivative with respect to t was minus tangent of 2 pi t. The second derivative takes you down to minus secant cubed of 2 pi t. And on Friday, we will actually come back and find what the equation of the tangent line is at the point where t equals minus 1/6. Okay, what would I like you to work on for next time? 10.1 basically. Get 10.1 done, and I'll be happy with that. And in your spare time, you could start looking at the yellow project. Any questions? Okay, see you all same time, same place, maybe on Friday for more derivatives of parametrized curves. Okay, have a good day.
You should not.